Let's look into the tests involving variances. Goals. We want to test if the variance of a population is equal to a given value. Suppose here H0 is that sigma square is equal to 4 and alternative will be sigma square not equal to 4. So we test for if the variance is equal to some standard value. We don't want the variance of something to be greater than some limit, so we want to test that. This kind of situation, it is as the one sample test of variance. We want to test if two populations have equal variances. Here H0 could be sigma square 1 equal to sigma square 2, and alternative could be it's not equal. Two sample comparison of variance, and we do it via F test. One sample test of variance, we do it via chi-squares. We want to test if two or more population means are equal by comparing two variance estimates calculated by different methods. This is called as ANOVA, analysis of variances. We are using variances here, but we are testing the equality of the means. So H0 could be mu1 equal to mu2, mu3, and whatever number of means are given. And the alternative could be that these means are different, or at least one of the means is different. Let's look into this one sample test of variance, where it is important, this variability. QC of drugs in stock exchanges, banking and investment sectors. We know that S square, that is the sample variance, is an unbiased estimate of sigma square, the population variance. So we have a statistic here, a parameter here. So this statistic can be used as an estimate for this parameter. If we have a sample coming from a normal population and we have repeated samples of size n, this factor n minus 1, we came through some equations, divided by this sigma square, that is this variance under the null, follows a chi-square distribution. So we'll do this test like this: n minus 1 into s square, this is the degrees of freedom, divided by the variance under the null, and the resultant thing is our chi-square calculated, and then we go on to the chi-square distribution and find the chi-square critical and compare this whatever we have obtained here, this number with this chi-square, and test for our hypothesis. Chi-square distribution, they are like T distributions, so there are many distributions and they are based on degrees of freedoms. They range from 0 to infinity. Looks like some mountain shape, seems like K2 or something, and it's not like the normal distribution, the bell curve, so there is no symmetry here. Central limit theorem does not apply for making inference about variances. However, the tests for normality are important. Statistical test for one sample test of variance, same like the we have seen in the Z's and T's. We formulate the hypothesis, then the hypothesis can be of any of these shapes. We are testing for some variance bigger than some variance under the null, and under the null we go for this variance, the sample variance is less than equal to and this sigma square naught, which is the variance under the null hypothesis. This is case 1. In case 2, we are testing for some variance less than some variance under the null, and null hypothesis is opposite to it. This is case 2. In case 3, we are looking for the inequality of variances in alternative hypothesis versus they are equal in the null hypothesis. We determine n, we set alpha. Normally alpha is set at 0.05, and then we determine the test statistic. So we have seen previously the test statistics like z calculated or t calculated. So here what we get is chi-square calculated. So there is chi-square, letter chi in Greek, and this is similar to letter x. Since we are testing for the population, so this Greek letters or a parameter symbol is used, and for the samples we will be using the x square. We determine the rejection region. We go to this chi-square table for that particular degrees of freedom, which we calculate from n. Based upon that alpha, we look into this chi-square critical. So that is our rejection region. In order to reject the null hypothesis towards right side, we should have the chi-square calculated greater than the chi-square critical. In order to determine the rejection region for one-tailed test, we should have this chi-square upper particular degrees of freedom and that particular alpha, and for a one tail to the right we will use this chi-square upper, and for a one tail to the left we will be using this chi-square lower, and at that particular alpha and degrees of freedom for both of them at alpha by 2. We will split alpha into 2 and we will calculate both this chi-square in the upper tail and the lower tail. Fail to reject based upon if in a right tail test the chi-square calculated is greater than chi-square which we calculated at this alpha and degrees of freedom, the upper one. And in case of case 2, we will reject the null hypothesis if our chi-square calculated is less than chi-square for lower one, the left tail one, and we reject the null hypothesis if chi-square calculated on the respective tail, whether the right tail in a two-tail test, whether it is towards right or left, depends where your calculated number is. So it should be greater than the chi-square upper at that particular alpha by 2 in case your calculated is greater than the this critical, or in case of the smaller numbers we will look for the left tail. So in that case this chi-square calculated should be less than the this lower chi-square critical. And finally we will conclude with the statement. Chi-square can be calculated in Microsoft Excel as well. The function is chi-inverse, and in this chi-inverse you give him alpha and degrees of freedom and you will get this chi-square critical for a given value of alpha. Same way you can solve this with chi-dist. In chi-dist you need to give the Excel the calculated chi-square and at that particular degrees of freedom, so that will give you the probability of seeing this chi-square in the distribution, in the chi-square distribution, and this p-value should be less than alpha in order to reject the null hypothesis in case of a one-tail test to the right or left, or in case of the if you are doing a two-tail test, we will compare it with alpha by 2. So this is the chi-square table. Right now we are looking for the one-tail test, one tail to the right, and this is if its alpha is 0.05 and respective degrees of freedom. So you will go and you will calculate this chi-square critical from here. For example, if your degrees of freedom are 5, your alpha is 0.05, so your chi-square should be 11.07. if your alpha is 0.01, it should be 15.09. if you are checking it for the left tail, 1.15 here and 0.554 here for alpha at 0.01. Let's look this chi-square with some example. So here we do have a statistical test for one sample test of variance. We can stop it right